So last week we talked about the ring model. We talked about the ring model in two regimes. One regime in which the recurrent connections amplify the external input, and the second regime in which the recurrent connections are sufficiently strong as to break the symmetry of the dynamics such that a bump solution with a broken symmetry emerges even in the absence of an external input. There is a continuum of different bump solutions, and the external input, even if it's infinitesimally small, will choose the one of the bump solutions out of a continuum of possible bump solutions. This was last week. Any questions about that? So there was one thing that from the question that I received after class, one thing that seemed to be somewhat unclear to some of the students was the following thing: how do we compute the shape of the bump solution? So it was very clear that the homogeneous fixed point is unstable. This was easy to see, but and that something has to emerge. And the question is, what determines the shape of the bump? So I said that the shape of the bump is a cosine, a truncated cosine. This is something that looks like this. This is minus pi. This is pi, and this we denoted by theta. See the critical value of theta. So how can we compute the shape of the bump? Now the way to do it is actually pretty straightforward, and the idea is the following: we computed the input to the neurons given the pattern of activity of the entire network, and this was given by J0 A0 over 2. Now, in general, this could be a function of time, but we're thinking about the stationary solution plus the homogeneous external input plus J1 A1 over 2 cosine of theta, and there are two terms that don't enter here. One is the modulated external input, which we denoted by H. So this was H00, right? That was the notation. One that we denoted by H01, but we assume that it is equal to 0. And another one is B1, but we can define 0 such that B1 will be equal to 0, where A1 and B1 are the Fourier coefficients. Now, writing the fixed point equation, if this is the input, the fixed point equation, the dynamic is R dot is equal to minus R plus H, right? So the fixed point solution is simply R is equal to the threshold linear function of this input, R of theta. Now, if we know R of theta, we can compute A1. A1 is simply 1 over pi, an integral of R theta prime cosine of theta prime d theta prime. So we have two equations. We have A as a function of H, and H as a function of A. And by solving these two equations, if you want to write it this way, by solving these three equations, we can compute the value of theta c. And the resultant solution is not, I forgot the name in English, mishva'at stuma. How do you say it? I'm sorry? Couldn't hear you. Transcendental. It's a transcendental equation, but still it has we can solve it numerically and then find the value of theta c. Questions? So this is a leftover from last week. This bump solution is, as I said, there is a continuum of possible solutions. This is like the line attractor that we discussed when we were talking about working memory. And one can ask the question of what would happen if the parameters of the problem are not finely tuned. So in the working memory problem, in the case of line attractor, what are the consequences of mistuning the parameters of the connectivity? So the time constant, rather than being infinite, it will either be smaller than infinite, and then what will happen? The dynamics will converge to a fixed point and forget the initial state. Or the dynamics will diverge if a connectivity is too strong, or if more precisely, if the eigenvalue is too large. We can ask a similar question here. What will happen if connectivity is mistuned? The connectivity. So we assumed something about how neurons are connected. There was a rule. We said that the strength of connectivity between a pair of neurons is equal to a constant plus cosine of the functional angle between these neurons. The question is, what will happen if connectivity is mistuned in this case? What do we expect? No, I'm not talking about biology. We're all about the math. What do you mean? So perhaps we should be more precise. So we restrict our analysis to the case of the bump, because in the case of amplification, there's nothing that requires fine tuning. So we're talking about the bump state. So you're suggesting that if we mistune the parameters a little bit, the dynamics will diverge. Now, thinking more let's go back to the working memory problem. Okay, so in the working memory problem, so let's draw it. So let's say that this is our line attractor. So in the idealized line attractor, where everything is finely tuned, the dynamics will go in this direction. And if we start from any point here, we will stay here. Now, if we mistune the parameters, nothing will happen. Nothing interesting will happen in this direction. All the new things will be in this direction. So we expect that after mistuning, the dynamics will go in this direction or this direction. So the direction in which the ring model is finely tuned is not a direction of, it's not on the verge of divergence. This is not in the regime that is close to divergence. This is the instability is in the direction of, if this is our ring and this is our bump, the instability is in the direction of a symmetry of the problem. It's not, we don't, therefore, if we mistune the parameters, we don't expect that the whole bump will suddenly, that the whole dynamics will diverge. We expect interesting things to happen in this direction, in the direction of the bump. So what kind of things can we expect? Well, what's the current interval between the bumps? What's the current interval between the bumps? 0. It's a continuum, and we can have a bump in any angle. So when you say larger intervals, maybe you mean larger widths? Change in the width. Again, this is not a direction of instability. The direction of instability is the fact that we have a continuum of solutions. So what will happen to the continuum of solutions? Same way as here we had a continuum of solutions, and suddenly, as a result of the mistuning, maybe all solutions collapse to a single, let's say, to a single solution that either diverges or collapses to, let's say, a single solution here. So the answer is that the special thing about the bump solution and the special thing about the line attractor here is the fact that we have a continuum of solutions. The continuum of attractors of the dynamics. And once we mistune the parameters, this continuum of attractors disappear. So similarly here, if we mistune the parameters, we expect that this continuum of solutions along the bump will also disappear. How can it disappear? What kind of? Why should the solution be periodic? I don't see how a small change can eliminate A1. So maybe we should go back and ask what kind of perturbations or mistuning of the parameters we are willing to consider. So one natural thing is to remember that the ring is in fact discrete and not continuous. So in all our analysis, we started by drawing a discrete set of neurons, and then we said, okay, we're going to take the continuum limit, the limit of n, of infinite number of neurons, and we can ask the question, what would happen if this is for a discrete ring, for a ring that is composed of a finite number of neurons? What solution do we expect? Let's think about it in the framework of symmetries. In the continuous case, we have a symmetry to rotation. We can rotate the angle. We can rotate the problem at any angle, and the set of equations that will describe it will be identical. What about a discrete case? Let's say that we have only 4 neurons or 6 neurons. Is this problem invariant to any rotation? To any rotation of angle?
Then the bump would be separated by the angle over 6. And then when you switch it, we get the same.
So the symmetry now is discrete. So we can rotate it by 60 degrees, and we'll get exactly the same problem. But if we rotate it by 7 degrees, then we'll have a different problem. So the problem is no longer symmetric to a continuous rotation. It's now symmetric to a discrete rotation. So the set of solutions that we had here had a symmetry for a continuous to rotation. So what do we expect about the symmetry of the solution in this case? Of the set of solutions? To be discrete. So what's the meaning of a discrete but rather it will be what? I'm sorry? So we expect to have a finite set of fixed points. So in the case of a discrete ring, we expect that rather than having a continuous set of solutions, now we'll have a discrete set of fixed points, so there will be some stable fixed points, and in between, unstable fixed points. So going from the continuous space to discrete space, we will move from a line attractor to a discrete set of fixed points. So this is one example of one way in which this line attractor solution can be destroyed. Right? Taking a small number of neurons, and we expect that the larger the number of neurons in the network, the more fixed points we will have, that the number of stable fixed points bump like a stable fixed point will be linear in the number of neurons in the network. Perhaps the number of stable fixed points will be equal to the number of neurons in the network, and only in the limit we'll get something that looks like a continuous solution. Again, thinking about it using an energy energy formalism, or more perhaps energy-like intuition, we expect that if the number of neurons is small, the energy landscape will look something like this. This would be, I don't know, an example of 3 neurons. You have to remember that everything here is periodic because we're talking about angle. So maybe we have 3 stable fixed points and 3 unstable fixed points. And if we move to a much larger number of neurons, the energy landscape will look something like this, which is close to a flat energy landscape. So this is one type of perturbation that one may want to consider. Another type of perturbation, what do we expect if, let's say, these 2 neurons are, the strength of connection between these 2 neurons is larger than between any other pair of neurons? What kind of solution do we expect then? I mean, this is a perturbation of the connectivity that doesn't preserve the symmetry. Only these 2 neurons are connected with stronger connections than others. What kind of solution do we expect? I'm sorry? Then we expect that there will be only one fixed point that somehow is related to this breaking of the symmetry. And the stronger the perturbation, the connectivity, the less it will look like a continuum of bumps, or the smaller will be the time scale for convergence to this single fixed point solution. So we're thinking about the symmetries in the problem and how these symmetries are broken when we perturb the problem. We can understand something about the symmetries of the solution. There is another perturbation of the connectivity that we will spend some time discussing, and this is breaking or considering connectivity matrix that is no longer symmetric. What do we know about behavior when connectivity is symmetric? This is something we discussed several weeks ago. The dynamics will necessarily converge to a fixed point. And if the connectivity is not symmetric, well, then we don't know. We cannot say that it will not converge to a fixed point, but it's no longer guaranteed that the dynamics will converge to a fixed point. And soon we will discuss a perturbation that breaks that destroys the symmetric structure of the connectivity. But before considering this perturbation, I'd like to show you some rather recent experimental results that I think are very closely related to the to this ring model. Yes. Sure. Well, we yes and no, complicated. So we started by talking about OTAPs. We didn't start. I think this was the second example. So an OTAPs is we consider a single neuron, and we have a continuum solutions. So the problem was R dot is equal to minus R plus JR plus external input. And if J is equal to 1, then you have an integrator. Let's remove the H. If without the H, you have a continuum of solutions. So in principle, the answer is yes. This is an example that we discussed. It's more complicated when you consider the non-linearity of the neurons. So when people consider the non-linearity of neurons and thought about how you can generalize the ideas of a line attractor to non-linear neurons, typically the results are that the number of fixed points is equal to the number of neurons. Now, this doesn't seem to be a huge problem for our brain. I mean, we have enough neurons. If you take 10,000 neurons, and you consider all fixed points, this will look as if it is continuous. If you think about the goldfish oculomotor integrator, this is more problematic because there you have only 40 neurons in the network that is believed to underlie the integration. And then you expect to see the discreteness of the multiple fixed points. Did I address your answer? So the ring model was developed to explain selectivity in the cortex. However, several years ago, this was 2015, this paper came out in Nature talking about orientation, selectivity, and angular path integration in flies. And I will not have time to fully describe the paper, but I think it's pretty interesting, and I'll just say a few words about it. So this is how the experiment looks like. This is Mr. Fly, and it is standing on this ball that sits on air, so the fly can rotate this with its legs. This is visual input, and using virtual reality, the visual input can be can be controlled by the movements of the fly. And while the fly is doing its things, activity of neurons is imaged from above using a microscope. And the recording is done from a brain region that is known as the ellipsoid body, that is supposed to say something about the visual cues. And I would like to show you a few movies. So what you will see here, this is the fly. This is the visual input. And this is activity in this ellipsoid body. And what you can see is that the activity in the ellipsoid body tracks the angle of the visual input. And in fact, one can construct a decoder that uses this activity to decode the location of the visual input, and this is what you see here. Now, this is neural activity. There are several neurons here. And, well, as it turns out, these neurons, or the neurons that correspond to the location of the stimulus, they reside on something that physically looks like a ring. I mean, there's nothing in our model that tells us that neurons should reside on a ring. This is just a functional This is just a way of depicting it. But in this case, it seems to be that these neurons reside on the ring. And now, one question you could ask is, well, maybe these are just sensory neurons that respond to this stimulus. And to address this question, they used this stimulus, which is much more complicated. And if these are just sensory neurons, we expect that each of these bars will elicit its own pattern of activity in this ellipsoid body. But it turns out that this is not the case. The animal responds to the location of the stimulus irrespectively of the details, of the fine details of the stimulus. And this is how it looks. So again, we don't see several bumps of activity or several hotspots of activity. The activity corresponds to the azimuth of this object rather than to its microscopic features. And this is a fly on this foam ball. And another way of demonstrating it is now using two bars. Now, if activity is a reflection of the visual world, then we expect to see two bumps of activity, but we only see one. By the way, the number of neurons here, I don't know the number, but it's a small number. Certainly not a continuum. But in these invertebrates, it's not clear what's a functional unit, because it's not the rules of transmission of information are more complicated in invertebrates. And finally, what happens in the dark, in the absence of any visual input? It turns out that you see the same thing. You see this bump of activity, and the location of the bump of activity can be mapped to the angular direction of the fly as measured from the rotation of this ball. So this is how it looks. So there's no visual input here, where there's no input at all. And the fly is moving, and as if it is rotated, we can measure it by the rotation of this ball. And the location of this bump of activity corresponds to the predicted angle of the fly. No sensory input. We don't exactly understand all the details underlying or how this bump emerges in this fly, but I think that I find it pretty remarkable. Many of the predictions of the ring model manifest in the activity of the fly, the neural activity of the fly. Any questions? Yes. So, in the presence of input, I presented evidence that the activity in the ellipsoid body, the physical location of activity in the ellipsoid body is indicative of the azimuth of the visual stimulus. Remarkably, similar to the bump solution in the ring model, even in the absence of input, you have a bump of activity, and this bump of activity reflects or is a reflection of an integration of the location of the animal as measured by its rotating the ball. So in that sense. Did I answer your question? More questions? Okay. So what we will do now is we will go back to the to the ring model, but this time consider a perturbation to the connectivity such that connections are no longer symmetric. So the connectivity matrix that we will consider is the following. J of theta is equal to J0 plus J1 cosine of theta. This is a old connectivity matrix. And we add a term that is asymmetric. Plus epsilon J1 sine of theta. So if we consider neurons on the ring, this implies that connectivity in one direction is different from connectivity in the other direction, and we will consider the regime in which this asymmetry is very weak. We'll take the limit of epsilon being very small. We will consider the case of no external modulation. So all neurons in the network receive exactly the same input, and we will consider parameters that correspond to the ring solution. This is J1, I think, is larger than 2, and J0 is smaller than 1. So this is, we'll consider the regime in which we have the bump solution. Again, we have our set of equations. This time, I'm going to add the tau, because I will use it. Tau r dot is equal to minus r plus h, threshold linear of h, and h of theta and t is equal to an integral from minus pi to pi d theta prime over 2 pi j theta minus theta prime r theta prime and t plus the external input, which I forgot. What was the notation for external input? The constant h00 or something? So this is our model. This is our new model, where the only new thing here is this term. So if we write I don't know why we need 5 of these. Maybe 2. So the question is, what do you think will happen? What will happen if epsilon is equal to 0? Same as before, which means a bump. Okay, so let's say that we start with epsilon being equal to 0, and then suddenly we turn on epsilon. What will happen? The shape of the bump. Well, things will happen naturally. But if epsilon is small, then, well, in general, we'd expect that the shape will change by little. The larger the value of epsilon, the smaller would be the effect on the shape of the bump, if indeed there's a change in the shape of the bump. But this is not very, in some sense, this is not very interesting. The question is, will we see a qualitative difference in the behavior, in the solution? And this is something that we may expect, given the fact that the bump solution is a line attractor, is a manifold attractor, and therefore is very sensitive to changes, to any change in the parameters of the problem, which in some sense breaks the symmetry in the direction of the manifold of solutions. Let's look at this term. So this term is equal to an integral d theta prime over 2 pi j0 plus j1 cosine of theta minus theta prime plus epsilon j1 sine of theta minus theta prime r of theta prime and t. So we know that when epsilon is equal to 0, the solution is the bump solution. So let's draw the bump solution. So this would be, let's say, minus pi and pi. And let's try and use this to think about the effect of this perturbation on the solution. So we assume that we start with this bump solution, and we add this term to the connectivity. Let's continue after the break. Shall I turn on the air conditioning?
תמיד מתחלפים, תמיד קורה לי, אז רציתי לעשות את התסמינים.
שמעתי גם אם היא הייתה בקטנה שלי, אבל היא דווקא יותר מוזרה. לא, זה כאילו שם שהוא שונה כזה. אגב, השני שלי ממש קטן מהחלום, יש דור של 5 אנשים וחמם, והשם זה לא מתחילים לרב שכך.
אז בואי נאכל את הבאמבה שלי. זה באמבה קטנה, ונראה לי שזה בול, כי זה מין... נכון? אני חובבת אותה. בונג'ור. אני אני גוספת. מי זה?
אני ממש
סתם, היא ממש לא אמרה את כל זה. רק אמרה את אני גובה, ואז...
חמש דקות בדרך כלל שאני גובה, שאני רוצה לחמם את ארוחת צהריים. אני רוצה להגיד לך שאת הכי מפילה דברים שאני מכירה, ושספציפית הבקבוק שלך הוא מאוד רועש. וואי, זה נכון.
וזה לא קשור אבל זה היה.
גם הכל קשור באופן. אז אולי כדי לפתילה, הרבה דברים. כן, כל שיעור. תקשי תגידו.
ספציפית הוא באמת רועש. כאילו, ממש עושה... היום... איך את אפילו? וואו. היום פתח את המקצה של הקפה, הקפה או משהו, ואז המקצה, שזה מתכת אף לא אצבע וזה עושה רעש כמו גום.
אתם יודעים מה הדבר הכי רועש בעולם? ואני יודעת מסיבות לא טובות? לא.
הפעם.
לא. אתם לא שנפלו? לא. בקבוקי סודה שנופלים ממגש. זה הדבר הכי רועש בעולם. והיה... למה סתם כל זה? לא, זה היה, יצרתי במקום שיש לו 2 קומות, אוקיי? והוא מין קומה חיצונית כזאת, וקומה פנימית שהיא נמוכה יותר, ואז היה שולחן בקומה העליונה יותר, שהוא היה השולחן הכי כאילו מפונפן וכזה, אנשים שסופר אוהבים את עצמם ומזמינים כזה לאלכוהול ושצלח גבינות וכזה, וגם במקרים שבעלים כזה, ומצפים גם שאני כאילו אוהב אותם נורא או משהו, אני לא מכירה אותם. בקיצור, ממש כאלה מלחיצים, והם ישבו, זה היה בשולחן נמוך כזה, כאילו שהוא נמוך שאני צחקתי, והם הזמינו כמובן כולם סודות, אז היה לי כזה כמה בקבוקי סודה על המגש, ואז אני מתכופפת כדי זכוכית סודה, זהו, אז אוקיי, אז אני מתכופפת כדי לשים משהו, וצריך נופל בקבוק, וזה עשה רעש, כאילו ברמה שגם הקומה הפנימית הנמוכה יותר, כולם הסתכלו למעלה, כאילו לראות מה קורה שם, ואז, והוא לא נשבר, ואני הייתי ממש בשוק והייתי ממש שמחה, וכאילו היה לי לא נעים עם הרעש וזה, אבל בסדר, הוא לא נשבר באמת, והשניים אחרים נופלים. והאלה, הפוסטים הם בהתחלה נפלו, לא נורא, חמור ומסריף, מפילה דברים, ואז שהשניים אחרים נפלו, הם הסתכלו עליהם וכזה, מה הבעיה?
מה זה פה? מה זה? נורית לא טובה.
מה? הם נפלו. או, אחד מהם לא זוכרת, אבל זה היה כל כך רועש, ואני הפלתי דברים, זה לא שכאילו, אבל זה מגעי סודה האלה. זה מה? לא, פשוט הם נגדו שווי משקל על המגש,
כאילו שמגש אלומיניום שלי.
למה יש בגלל לי? אני ביקרתי פעם אחת לקחתי את זה.
וואי, מסורות הכל כך ככה, בשבילי שזה מטורף. אני הבן אדם חוץ שירותי.
נכון, וואי,
הייתי במשימת
אני לא רואה לעשות החיוך כזה, כשאת מעוצבנת, זה ממש מעצבן אותך וזה, אני לא רואה בא לפחות.
אז זהו, אז בסימנסקי הייתי.
לא משהו?
והייתי ממש...
בוא ותגיד על הפחות, כאילו, איך זה תגיד מזעזע. אוי, מה את מבינה את זה? זה לא טעים.
אני בדברים כאלה.
וואי, אני ממש שני נגיד. מה דעתך על הכיש? אז זה או שתגיד שזה בגלל שתגיד, אני אחרי הכינו לי אני גם לא אהבתי רצנים, אבל...
אז לא הייתה לי שום קומנטרי על מה הכי מזמינים, אוקיי? היה לי רק על כאילו האפטרמט שהם משאירים. כי הם היו הולכים, ואחרי שאני הבאתי, כן, ואחרי שאני הבאתי פיסי תינוק הטעם שלה, את כל הארוחת בוקר שהיא הזמינה, הכל היה מפוזר ברדיוס של איזה 2 מטר ממנו. הייתי צריכה לעשות סלט קצוץ מהרצפה. לא מטאטא, אני אומרת לך שחלטים, הכל כזה רטוב, הכל כזה לא עושה את זה. שישה את זה. נורא?
כן, זה באמת נורא. וואי, כאילו אני בחיים לא אוהבת צריך את זה. אבל ילדים זה באמת...
אפשר להחליף את הקפה בשוקו, הוא אוהב שוקו, אני לא רוצה את הקפה. כן, אין בעיה, איזה שוקו? יש לכם שוקולית? לא? אתה אוהב רק שוקולית, אז מחייבת. אולי אני אביא לך שוקולית, תכיני לו. תכיני לו! מי מצטערת עם שוקולית תכית? אנשים?
יש ממש אנשים.
אנשים? מה? זה
לא, זה מוזר.
זה ממש מוזר.
אני אביא לך שוקולית, תכינו לי שוקולית שבת.
שיש לו שוקולית, זה מעולה הגיוני.
אבל מה תעשה איתו אם לא לבקשים מבצריות?
לא, אבל מרגע שהיא אומרת, אני
נכון.
מזמנת ממך שוקו, כאילו, היא יכולה להגיד, אני מזמנת שוקו, רק אני רוצה את ההפקעה הזאת.
זהו, אז כאילו, אז לא, אז זה היה כזה...
זה גם לא הגיוני. למה?
עכשיו במקום קפה, לראות
ביקור, אני אביא שוקו, אני עם ההפקעה שאני הבאתי חלב רגיל, אז קחו בבקשה חלב הזה.
אבל זה לא טוב, כי המסעדה לא יכולה לקחת אחריות על דבר הזה. כאילו, זה תביעת ענק. צריך שהוא לא שותף מספיק טוב את זה.
שכל פעם מישהו אחר יושב בכיתות או יוצא החוצה, ולפעמים היה שבכיתות
לא,
אני יודעת
מישהו
שאני
יושב
יוצא
לחוץ.
שבן אדם יוצא החוצה ולא יושב בכיתות, זה מרגיש טוב לבקר את אלה שכן יושבים. אבל אתה גם יושב.
אני חושבת שיש משהו מתחת לפני הספר שאנחנו לא יודעים כרגע. לא, את הבנאדה התפרצה.
כדאי, כי כל הזמן מפקרים אותי.
על מה?
וואו, מה קרה פה?
מה אמרו לך? יושבת פה.
פשוט הרגיש לה מאוד לבד, כולנו נשארנו.
נכון.
זה הקפה שלו. היום אני התפרצתי על אמא שלי, אחרי שהיא גזינה את הספר במשך חודש וכמה דקות טובות על הספר, ואיך חשבתי פה אמרתי, אמא, די.
זה בטוח שמענו אותך מפגישה כאילו?
כן. והיא כאילו לא, היא לא קולטה שזה היה מעצבן, ובגלל זה אני כאילו אומרת לה, היא כאילו, אני דואגת לך, זה מאוד חשוב, אני שמחה שאני מאוד מתרגשת, מה היית ככה בזה ספר הזה?
לא התפרצת פעמים ממש כמו
רק איזה ספר.
אין לי מושג. אני לא יודעת מה הנושא. תזונה, לא יודעת, משהו על מעיים תזונה. יופי לך, אתה בקראת הספר נורא נהנה. די, זה לא.
אני יודעת מה צריכה לעשות, את צריכה למצוא איזה ספר ממש משעמם על מוח כזה, ולחפור לה שהיא ממש צריכה לקרוא אותו, ושזה ממש כאילו, ממש חייבת. והיא תגיד לך כאילו תודה, אבל לא, ותמשיך.
אבל אני
לילה, זה ספרים וזה מה?
אני שונאת ממש.
לא, אני נצטרך ולא קומפלט.
מה קרה ביום?
כי אני ככה מטילה אחריות.
אני פשוט עצבנית על העובדה שתמיד ניסים לי על ספרי עיון כאלה.
כן, אבל זה כתובה, אני ממש לא מבינה. לשנות שם.
אין לי כמובן, כן.
אבל לא הספקת.
למה? די. אני לומדת מספיק כל השבוע, ואני באה לראות ספר, אולי בא לי שזה לא יהיה.
זה הרבה יותר על
הביולוגיה שלך, לא תודה, כאילו אולי אני רוצה לענות כל זה. אני לא יכולה לקרוא את הספר שלו.
סבתא שלי ממליצה על ספרים לפלסטרים עיוניים, ספרים לביקורת, והיא ממש ממליצה, אבל היא ממליצה בקטע של א' ממש כזה להיות בשוק שעוד לא קראתי את זה, כאילו כל פעם בשוק מהחורים
לא
שכל
קראתי
יום
את זה,
לא, 4 דקות? לא, זה לא ספרים קלאסיים, אני ממש בשוק שלא קראתי, ובקטע של את חייבת לקרוא, חייבת, לקרוא, חובה, כאילו אני לא חייבת לקרוא, זה מיליון ספרים עכשיו שאני חייבת לקרוא אותם, כאילו אני לא בסדר.
הקטע הוא שכאילו התקבעה אצל הראש שלי מינית לתפיסה שאני קוראת המון ספרים. עכשיו זה היה נכון, זה היה פעם דבר שנכון בכיתה ח'. עכשיו זה כבר לא נכון, כי כבר אין לי, כשאני רוצה לא ללמוד, אז אני פותחת בטלוויזיה, זה מה שקורה.
ג'ונתן.
ממש לא בא לי. לא.
Each one twice.
Yeah, each one. I gave you only one, so...
start. So we are talking about the ring model. This time when connectivity is not exactly symmetric, it's almost symmetric, but not exactly. We have this additional term. We assume that epsilon is very small, and we would like to understand what will be the effect of this term on the solution. So we can start doing the math, but it's often helpful and useful to solve it before solving any equation, getting an understanding of what will happen. The way to think about it is the following. Let's assume that we start with this bump solution and with epsilon being equal to 0. In this case, the bump will stay. There will be no. We already know that this is a fixed-point solution of the dynamics. So let's assume that we start with this fixed-point solution, and now we add this term. How will this term affect the activity of the neurons? Let's look at a neuron. Let's look at a neuron that is here, for example. Let's look at a neuron that is here. Let's consider one neuron here. What will be the effect of this additional term? So this is, we're thinking about neuron theta. And previously, neuron theta received input from all other neurons through this term. Now, neuron theta receives input from all other neurons through this term, plus a small input through this term. This is an input that averages the activities of all other neurons in the network with this weighting. Epsilon j1 sine of theta minus theta prime. So let's look at the neuron here. Let's say that theta prime is here. How will activity here affect the state of this neuron? Let's just think about this one, this particular one. How will it affect all other? How will this neuron affect this neuron? Why a little? Okay, I would like to. Well, it will be effect will be small because of this epsilon, but will it increase its activity or decrease its activity, or have no effect? Yes. Well, theta minus theta prime is negative because theta prime is larger. So this is a negative term. In the other direction? Well, no, because this is equal to 0. This neuron, the activity of this neuron is 0. So this term, this particular neuron will have no effect. The adding of this term will have no effect on this one, because this is equal to 0. Okay, and also this one will have no effect, and this one, clearly, right? All neurons that are 0 will have no effect. No, the story that we are telling now is the following. We have a bump solution. We add connection, and we see what will be the effect. What about this neuron? Or this neuron? How will these neurons affect this particular neuron? So for these, theta minus theta prime is positive. the activity of the neurons is positive. So we expect that this term will increase. This will increase the activity here. Let's use a different color. So the input here will be larger than it was before. Now we don't know whether it will be sufficiently large to generate activity here. Remember that we have a threshold non-linearity. So maybe it used to be negative, it will continue being negative, but to a lesser extent. But we know that for a neuron that is exactly here, we expect that the activity of this neuron will now become positive. So we expect that the activity of this neuron will go up. The one that was previously 0 but on the verge will now be positive. Let's consider this neurons that are here. What will happen to neurons that are here? Well, we can play the same trick. Okay, now let's say that this is theta. And let's say that this is theta prime. So this will make a negative contribution. And well, this could have made a positive contribution, but r is equal to 0. So there's no contribution. So overall, the input, the contribution will be negative here. Now it used to be 0, so it will continue being 0. What about a neuron that is here, that was very close to 0? What will happen to this neuron? Well, it will become 0. So thinking about it this way, we expect that the contribution of this would be to move these down, to move this part of the bump down and move this part up. So naively, we expect that the bump will shift a little bit. Just a little bit. Okay. So if the bump shifts a little bit, what will happen next? The same thing, because now this is the new bump. So everything that we considered here is true again. So the bump will shift again. So what do we expect that will happen over time? We expect we expect a solution to be periodic, as you proposed in the first hour. So this is a kind of perturbation that is expected to result in a bump that is moving, and since we have periodic boundary conditions, we expect the bump to move on a ring. So we expect that the solution will be a periodic solution, a limit cycle solution of a bump that is moving along the ring. This is the idea. Questions? Okay, so from this analysis, we expect that the solution will be a bump that moves along the ring. Now, we know that for epsilon being equal to 0, the bump will be stationary. And there is no reason to assume that there will be a large effect on the shape of the bump, because the perturbation is small. When you can imagine the case where the movement of the bump is infinitesimally slow, if epsilon is sufficiently small. So the question, what will happen if sufficient amount of time elapses? Now, the question is, what will it affect? Will it affect the location of the bump or its shape? I'm going to argue that the effect on the shape will be small. Now, I will prove it. But it's always, as I said, it's useful to first to understand it. The time it takes the bump to converge to its shape is determined by tau. We don't have by tau. The time it takes the bump to move will be determined by epsilon. We know that when epsilon is equal to 0, then there's no movement, and we expect that for infinitesimally small epsilon, the speed of motion of the bump will be infinitesimally slow. So we expect that this would be, the convergence to the shape of the bump would be much faster than the speed, if epsilon is sufficiently small. This is intuition. Okay? Okay. So we hypothesize that the solution to this set of equations is a bump that is rotating on a ring. And to prove it, we're going to consider this solution. We're going to consider this solution and prove that indeed it solves the set of equations. That's the deal. Questions? So we're going to consider the solution S of theta and t is equal to S of theta minus WT. This is a solution that we're going to consider. Now, clearly, this is an equation of something that is moving along the ring periodically. So the value or the pattern of activity, sorry. Let's use these notations. So the activity of a neuron theta at time t is equal to some function r of theta minus WT. I'm going to use this variable theta prime is equal to theta prime, theta 2 prime is equal to theta prime minus WT. And then R of theta and T is equal to R of theta prime. I'm going to guess this solution and show that indeed it solves the set of equations. Now, way to think about this solution is, so previously we were thinking about a bump on a ring. We can think about a bump that is moving along the ring, or we can think about a set of coordinates that is moving periodically. So in this set of coordinates that is moving periodically, we'll have a stationary bump. This is like thinking about in a relative to the sun. If we're thinking about set of coordinates that moves with a periodicity of 24 hours, I'm stationary. If we use a set of coordinates of the sun, then I'm moving very fast, both around the sun, but also around the axis of Earth. But we can think about a set of coordinates that moves with the rotation of Earth, and then in this set of coordinates I'm stationary. And similarly here, we will think about a set of coordinates that moves with this speed, with this angular speed w, and in this set of coordinates we will consider a stationary bundle. Questions? Okay, so now we can think about this. Now we can think about this term, which would be the input from the recurrent connections. And rather than integrating in the coordinates of theta prime, we will use the rotating coordinates theta prime prime. And then this will be equal to an integral d theta prime prime over 2 pi j0 plus j1 cosine of theta minus theta prime prime minus wt. Let's say, don't need more space, so this will be j0 plus j1 cosine of theta minus theta prime. I'm going to replace theta prime with theta prime prime plus wt, so this will be minus theta prime minus wt plus epsilon, thank you, plus epsilon j1 sine of theta minus theta prime prime minus wt, and this will be times r of theta prime prime. So this would be the input from the recurrent connections. Questions? So we have, the next step would be to open the cosine and sine using the basic trigonometrical identities. So cosine of theta minus wt minus theta prime prime would be equal to cosine of theta minus wt cosine of theta prime prime plus sine of theta minus wt times sine of theta prime prime. And similarly, we have a term for sine. Sine of theta minus wt minus theta prime prime is equal to sine of theta minus wt cosine of theta prime prime minus sine of cosine of theta minus wt sine of theta prime prime. And now we need to do this integration as before. Now I'm going to, I don't remember if I've already said it, I'm going to well, I said it, but I didn't repeat it, that we're going to consider a solution, R, which is the original bump solution. So we're going to assume that changes in the shape of R are relatively small, relative with respect to epsilon, and this will become explicit in a second. So I'm going to consider R, which is the original bump solution. In order to solve this integral, we will need to consider an integral of this term and an integral of this term. And I'm going to start with an integral with the first term. So let me do it here. An integral of cosine of theta minus theta prime So we have here two terms, right? We have the first term and we have the second term. What can we say about the first term? So this integral will have two contributions, one from the first term and one from the second term. So let's consider the first term first. So we have the cosine of theta minus wt, because it's outside the integral. And then we have an integral of cosine theta prime prime times r theta prime prime. Fourier, remember? So an integral of cosine of theta prime prime r theta prime prime. Integral from minus pi to pi, yes, over all neurons. So this would be equal to a 1 over 2. Let's write it here. Cosine of theta minus wt times a1 over 2. What about the second term? What about the second integral? So we have a sine of theta minus wt, sine of theta minus wt. Now we are considering, this is our bump. This is our function r. So our bump is symmetric, and therefore B1 is equal to 0. So we don't have a contribution from the second term. Let me repeat it. So the original bump is symmetric relative to 0. The original bump is symmetric relative to 0, and therefore B1 is equal to 0. So the second integral will make no contribution. Okay, we'll have another one, 1 over 2 pi, from minus pi, 2 pi of sine of theta minus theta prime minus wt times r of theta prime prime d theta prime prime. Again, this term will not contribute anything, so we're only left with this term, but this time with a sign. So taken together, the input will be equal to J0 A0 over 2 plus H00. This is the DC component plus J1 A1 over 2 cosine of theta minus WT plus epsilon J1 A1 over 2 sine of theta minus WT. Questions? So this is a contribution. This is a contribution coming from the perturbation. This is what we had previously. So I'm going to we'll do it in a second. So more generally, the equation that we were considering was R dot is equal to tau R dot is equal to minus R plus the non-linearity of H. Now, looking at this right term part of the equation, we have that this is equal to minus R plus G different way. I'm going to denote by H tilde, I'm going to denote this part. This is J0 A0 over 2 plus H00 plus J1 A1 over 2 cosine of theta minus WT. So this is H tilde is the input of the unperturbed network. So the true input is this input H tilde plus a small correction. So G of H is equal to G of h tilde plus epsilon j1 a1 over 2 sine of theta minus wt. So the input is the original input plus a small perturbation. So what can I do with this information? Taylor. I can Taylor expand it around h tilde. So let's do it. So this is asymptotically equal to g of h tilde plus g prime of h tilde times epsilon j1 a1 over 2 sine of theta minus wt. Why is it useful with respect to this equation, this Taylor expansion? What can we say about g of h tilde? What can we say about g of h tilde with respect to minus r? It's equal to r at a fixed point. So this term and this term will vanish. So the right-hand side of the equation will be equal to g prime of h tilde of theta minus wt times epsilon j1 a1 over 2 sine of theta minus wt. The right-hand side of this equation is equal to this term, to this perturbed term. Okay. Okay, now we can look at the left-hand side of the equation. This is the equation. So we can use a chain rule and write it as tau d to d theta minus wt of r theta minus wt times d dt theta minus wt. equal to minus W tau R prime of theta minus WT. Now R theta minus WT is just equal to G of H tilde theta minus WT. So R prime of theta minus WT equal to G prime of H tilde of theta minus WT times D of D theta minus WT of H tilde of theta minus WT. So what's the derivative of H tilde with respect to theta minus WT? This would be just minus J1A1 over 2 sine of theta minus WT. So this is just equal to G prime of H tilde times J1 A1 over 2 sine of theta minus WT, and there is a minus. So this is the left-hand side of the equation. So the left-hand side of the equation is equal to W tau G prime of H tilde J1 A1 over 2 sine of theta minus WT. Left-hand side, this is the right-hand side of the equation, and clearly the left-hand side of the equation should be equal to the right-hand side of the equation. So let's see. We have this term, which is here. We have J1 here, A1 over 2 here, and sine over here. So this implies that W tau is equal to epsilon, or that W is equal to epsilon over tau. That's easy, right? It also makes sense. So tau is a time scale of the dynamics. Epsilon is a magnitude of the perturbation in the connectivity. And the speed of propagation is just equal to, or the angular speed of propagation just equal to epsilon over tau. Going back to your question about the change in the shape. Where does the change in the shape of the bump as a result of this additional term in the connectivity, where does it enter? I'm sorry? What will be the magnitude of the effect, or how come that we don't see it? This will be higher order terms in epsilon. So in principle, when we did the Taylor expansion, we only took first order terms. The change in the shape of the bump will be a second order correction. Well, it will be it will affect the speed as a second order correction in epsilon. So this is an example of a moving bump. And going back to our poor fly, where we saw that there's a change in its case, the bump of activity is moving even in the absence of visual input. We can think about this as a mechanism of generating. Sorry, this is a way of generating a moving bump. We can also think about it as a way of starting to use a bump as an integrator. If we can control the speed of the bump, then we can use the bump as an integrator. Not clear that this is the right way of doing it by changing the connectivity, but this is like a first example where we see how a bump can be, in principle, used to integrate inputs. Questions about the bump? So this concludes our chapter on representations and also on line attractors. And starting on Thursday, I will talk about working memory and models for working memory. See you on Thursday.
יש יחס פה, רוצה שזה יהיה הפרעה, צריך שכל האיבר הזה יהיה קטן מהאיבר הזה. אבל בגלל שכאילו קוסינוס נגיד פאי חלקי 2 זה לא יקרה. יש אזורים שבהם הדרישה שזה יהיה איבר קטן מאוד היא לא תקפה. אוברול יהיה מאוד קשה.
במקום שבו...
לא צריך אוברול, אתה צריך בשביל הטיעון, שהטיעון יהיה תקף.
לא, כי אתה עושה אינטגרל. כל המקומות שבהם השיעוריות משפיעה בתוך האינטגרל.
רק בתוך האינטגרל? כן. הטיעון האינטואיטיבי שלך הוא היה נקודתי, הוא לא היה בתוך האינטגרל, לכן שם זה פרעי.
כן.
יותר אוברול זה...
כן.
אמרנו שזה שווה לזה רק שהנגזרת שווה לאפס.
לא, זאת משוואה. גרף שמאל של משוואה.
לא, אלה. זה שווה לזה, שווים אחד לשני, אנחנו משהו לזה אחר כך. רק שזה שווה לאפס. אז גם אנחנו
אתה לוקח במערכת הקואורדינטות הזזה, אז זה R, זה ה-R האנטוטר, וזה G של H. עכשיו G של H יש לו שני חלקים, יש לו G של H האנטוטר, ואז ייתן לך את הבאמפ האנטוטר, זה ילך עם זה. ואז זה נשאר עם התיקון, והתיקון הזה ילך עם זה.
בגלל המזגן, כולם בחוץ. הוא אמר שנעבור את זה בבית נראה לי. אבל
כאילו, הוא טוען, אוי כבר הלכתי לאיבוד, יש כל כך הרבה סימונים שהכל מספר לי.
מה שאמרת שזה הרגיל, הרגיל שווה לבנק.
נכון.
זה שווה לבנק שלנו, זה אמור להיות עכשיו הבנק. הרגיל, עוד הפרטובציה. אז זה בעצם שווה לזה. בגלל ששניהם מייצגים את הבנק הרגיל, ועוד הפרטובציה של הבנק. אז אנחנו נשארים זה שווה לזה.
לא חיובי לי. הוא אומר זה שווה לאפס בעצם.
לא, זה שווה ל-R.
זה שווה ל-R? נכון. זה תמיד שווה ל-R.
למה?
זה הגדרה של R, הרי.
R שווה ל...
G של H, זה כאילו עם Non-Linearity, לא?
נכון. Yes, I can.